In the previous video, we applied a signal, Vm cos omega t, to our circuit composed of a resistor and an inductor, and we found the output current was given by the equation shown here. What we'd like to do now is apply a complex voltage at the input and determine what the output is going to be. But before doing that, I want to go over some background material that is going to help us understand what it is that we're doing. To do that, I'd like to simplify our output current I of t as simply the magnitude of whatever that output current is times the cosine of omega t plus the phase that the current is offset from the input voltage. Now we're dealing with linear time invariant circuits, and they have a couple of features that you've probably noticed by now. The first property of interest is the scaling property, and the scaling property states that if I was to scale the input by a constant, the output would be scaled by exactly the same constant. So if my input was equal to V of t, which is now going to be k times Vm cos omega t, then the resulting output will be I of t, and that will be simply k times whatever output I would have had before, which was Im cos omega t plus whatever phase shift we'd encountered before. Notice that as I scale the amplitude, the frequency doesn't change and the phase doesn't change either. The second important property is the delay. If I delay the input, the output will naturally be delayed. The input, V of t, is now equal to Vm cos omega t minus some delay, which we'll indicate as this way. Then our output, I of t, will be simply equal to the output we had before, Im cos omega t, plus whatever phase shift we had before, plus whatever phase delay we applied at the input. I can take those two features and use them to adjust my input. I can have a phase shift of 90 degrees. If I happen to pick phase is equal to 90 degrees, then V of t will be equal to Vm cos omega t minus 90 degrees, and I of t will be equal to Im cos omega t plus whatever phase shift I had minus 90 degrees. But we know the first term here, V of t, can be written as Vm sine of omega t, because sine function is simply a cosine function delayed by 90 degrees. Likewise, the current will now be written as Im sine of omega t plus whatever phase shift the current was subject to previously. The next interesting thing I can do is have a value of k. K, our scaling constant, is simply equal to j, where j is equal to the square root of minus 1, or an imaginary number. Some of you might think of it as the letter I instead. In circuits, we tend to prefer the letter j because I is already taken for current. Now in this case then, V of t will be equal to j times Vm sine omega t, and the resulting output, I of t, will be equal to j I sub m sine omega t plus, again, that same phase shift we had before. The important point to note here is we started with a real input and we got a real output. When we have an imaginary input, we get an imaginary output. In other words, real inputs cause real outputs, and imaginary inputs cause imaginary outputs. What else would we expect? Now let's combine the two inputs to have our input signal now V of t will be equal to Vm cos omega t plus the imaginary part now j times Vm sine omega t. And we know from the above, and from the concept of superposition, that the output will simply be the sum due to the two inputs acting alone. I of t will be equal to Im cos omega t plus the phase shift that it will experience, plus j times Im sine omega t plus, again, the same phase shift. Mathematically, we can apply such a function to a circuit, and we know based on superposition that the input that was real will give rise to the real output, and the imaginary input will give rise to an imaginary output. We can't really do this in practice, but mathematically we can apply it, and this turns out to lead to a very convenient way to represent signals. In particular, if you recall, Euler's identity allows us to write now V of t will be equal to Vm e to the j omega t, and I of t will be equal to Im e to the j omega t plus our angle. We're going to use this in the next video and see how that simplifies the analysis, in particular all the integrals and derivatives that we have to take when we analyze a circuit driven by a sinusoidal source.